Well, we're near the end of the course, but that means that the exams are just around the corner. So we thought that for this program, we'd look at a few of the types of questions that are likely to crop up in the exam, and just to talk about how we go about answering them. Now, the questions are going to be a mixture of theory and example, the example carrying on from the theory you've just written down. So, to begin with, a typical theory-type question could be something like this. State Cauchy's formula. So, you've got to remember how to write that down. But to make things a little easier for myself, what I do is I try and place where I saw that formula in the course. Now, remember that that was one of the major consequences of Cauchy's theorem. So it's going to involve an integral around a contour. And in this case, the contour is a circle. So I can start writing it down. The formula tells me something about the value of a function f at some point A inside this circle. So f at A is equal to what? Well, I know that it's the integral around the circle. I want the value of the function at points on this circle. And now I've got to work the A into this formula, and I remember that I do that by dividing through by z minus A. Now there's always a 2 pi I floating around in these, and if I put it on this side, it's in the form 1 over 2 pi I. And that's the formula written down, but I haven't finished yet. It's very important to remember to write down the conditions under which this result holds. And in this case, the conditions are that f is analytic. And it's analytic on some region R that contains the circle. Okay, so that's Cauchy's formula written down, and a couple of marks in the back. Well, a typical question will then have an example following on from this theory. So for Cauchy's formula that we just written down, you might get something like this. Now that's a pretty horrible integral. But notice it's a real integral, and I want to evaluate it using a complex integral. And in the case of something as messy as this, you'll be given a hint. Okay, so there you're given the complex integral that you have to use. It's the integral of Ez over z around the unit circle. So now I can immediately go off and use what I've been given. I've got the starting point, I've written down Cauchy's formula. The hints told me which complex integral to look at, so what I have is this. There's Cauchy's formula that I've just written down. The integral that I've been told to look at is just e to the z over z. And now I've simply got to relate that to the formula. What am I going to choose for my f of z? Well, it's the thing on the top, so f of z is just e to the z. Now I have to pick my point A. Well, all I've got down here is z, so that fixes A as simply being 0. Now on the left-hand side, I want to evaluate f of A. That's f of 0, which in this case is e to the 0, which is just 1. So to relate the integral in the hint to Cauchy's formula, all I've got to do is put this in, and I have 1 is 1 over 2 pi I, that complex integral. Now, I'm trying to get towards that real integral, and I know the way to do that is to somehow unravel this complex function into a real and imaginary part. Now, to do that, I have to choose a parameterization. And since that I'm on the unit circle, I'll choose the obvious one. On C, I'll let z be e to the I theta. And I want to get all the way around the circle, so theta is going to run from 0 to 2 pi. Now in the formula I've got a dz, so to get that in terms of d theta, I note that that's I e to the I theta d theta. And now all I've got to do is plug this into that. I'll take the 2 pi I over on that side, so I have 2 pi I equals the integral around the circle, that's from 0 to 2 pi, e to the z, which is e to the I theta, over z, that's another e to the I theta, dz, which is, in this case, I e to the I theta d theta. I can do a bit of cancelling. The i's will go, that will go. And what I'm left with is the integral e to the I theta, and I want to unravel that into a real and imaginary part. And you see that I'm almost home and dry, because I know e to the I theta I can write in terms of cos and sine. Then I can do that again for this e here. And I'm pretty well assured that I'm going to get one of the real or imaginary parts looking like the real integral that I was asked to evaluate. Well, we've asked you to go through the details in the broadcast notes after the program, but what happens is that you'll find that it's the real part of this, which is the integral you're after, and so the answer is just 2 pi. So that's a typical type of question. A bit of theory followed by an example that builds on the theory you've just written down. Now for the theory, you've got to remember how to write down Cauchy's formula. I make things easier by trying to remember where it was in the course. For the example, what you want is a chain of ideas. You want a starting point so that this gets you into the solution and you carry along through the solution, and the algebra almost takes care of itself. Well, for a more difficult type of theory question, I've asked Graham to have a go at answering just such a thing.
Well, I'd like to develop the idea that Tim just mentioned and develop a sort of strategy for revising and for tackling problems. Now imagine that you're sitting in the examination room and you get a problem something like this one. Right, so the first part of the question is state Taylor's theorem. Well, how do you get that out of your memory? How do you remember the statement of Taylor's theorem? Well, I think everybody remembers the formula for Taylor's series. It's f of z equals f at a plus f dashed at a times z minus a plus f double dashed at a times z minus a squared. And don't forget the 2 factorial, and so on like that. Now, you can actually use this to remember the conditions for the theorem as well, because what about the function f? Well, all our functions have got to be analytic on a region, so we'll say if f is analytic on a region R, say. What about A? We must mention A somewhere. Well, A had better lie in R, so we have and A lies in R. Then we've got this series, then. But where's the series convergent? Well, it's convergent in a disk. So it's in any disk. Well, not quite any disk. It's got to be centered at A, of course. Any disk, center A. No, that's not quite right, because the disk has got to lie in R. So any disk, center A, in R. That's the statement, then, of Taylor's theorem. And I can dig up the conditions, I can remember the conditions, as soon as I can write down the form of the series. Let's look now at the next part of the question. So we've got to prove the special case of Taylor's theorem for an expansion about the origin. Well, this is the theorem that's sometimes called Maclaurin's theorem, and I guess that we're given this one because it's a little bit easier to prove than the general form of Taylor's theorem. So the series now is going to look like this. It's going to be f of z equals f at 0 plus f dashed at 0 times z plus f dash double dashed at 0 z squared over 2 factorial, and so on. And that's going to converge in a disk. Now, the disk is going to be centered at the origin. Well, if we're going to talk about convergence of a series like this, then it's pretty clear we're going to have to look at a finite sum plus a remainder. and the whole business is to show that the remainder tends to 0. That's the whole point of the exercise. Now, when you're presented with something like that, you need a starting point. You need to remember the starting point for the proof of this theorem. And the starting point is very easy to remember. It's, in fact, Cauchy's integral formula, the one that Tim was talking about a moment ago. So it's this. You can see why, can't you? Because you start with an f of z on both of these series and the integral formula. So integral around C, that's the circle, I suppose, f of w. I've got to use a w because I've already used z over w minus z dw. Now, the idea is to push this and shove it until you get a series out of it. Now, how could you do that? Well, it's pretty hopeless to try and get a series from the f of w bit. I mean, that's virtually asking you to state Taylor's theorem, isn't it? So the only bit that you can do anything with is the 1 over w minus z. So you've got to do something with 1 over w minus z. You want a series for it. Well, you probably don't remember a series for that, but you probably do remember a series for 1 over 1 minus alpha. That's the well-known geometric series. It's the easiest series of the lot. 1 plus alpha squared, and so on. Now, that won't quite do, because we need to consider the remainder. We're talking about this term, you see. So we need a series, not an infinite series, but a series with remainder. Well, I'm sure you remember the geometric series from your school days for a finite number of terms. So suppose we go as far as alpha to the power n. That sum is 1 minus alpha to the n plus 1 over 1 minus alpha. That's the sum to n terms of a geometric series. Now, I can rearrange that term by taking off the alpha to the n plus 1 and putting it over the other side to give me the sort of series that I want, you see. I can go up as far as alpha to the n there, then add on the end this term, which is alpha to the n plus 1 over 1 minus alpha, and that's the sort of series we need. Now, all you've got to do now is to manipulate this 1 over w minus z until it looks like a 1 over 1 minus alpha. Well, the obvious thing to do is to take out a 1 over w. So you don't really have a choice. You've virtually got to do that. So it's 1 over w times 1 over 1 minus z over w. And now we've got the sort of series we need. The first terms are going to be this finite sum with alpha, z over w in place of alpha. So I won't bother to write all that lot out. It's simply n terms to go in there. The important thing as far as we're concerned is the last term, this remainder thing. So it's alpha is now z over w. So z over w to the power n plus 1 over 1 minus alpha, which is z over w. So that's the finite series. Now, why did you need that? Well, you needed it because you wanted to stick that lot into the integral and turn that into a series. Now, I've done that already, and here it is. There's the bit that I had in square brackets. It looks horrific, but it's nowhere near as bad as it looks, actually. There's the finite sum. There's the bit that corresponds to the remainder. Now, we've got two things to check. We've got to check that this sum gives us the Maclaurin series, the terms in the Maclaurin series, and this bit we've got to make very small when n is very large. So let's start then with this finite series and check that we've got the right sort of terms, and we'll do the easy one first. The first term, which is f of w times 1 over w dw, the integral of that. Well, it's 1 over 2 pi I, the integral around the contour, f of w over w dw. What's that equal to? Well, that's easy. That's simply Cauchy's integral formula, so that's f at 0. Well, of course, it better be. If it isn't f at 0, then we've made a mistake, because we know what we've got to get from that term. It's got to be the first term from the Maclaurin series. Now, the term with z to the n in it. Well, that corresponds to this integral, 1 over 2 pi I, picking up that term, you see, from the series, integral around C, f of w. Now, the power of w underneath will be, there's 1 there, n there, so it gives us w to the n plus 1 dw. Oh, I've forgotten the z to the n. There's a z to the n that comes right through the integral because we're integrating with respect to w. So we've got a z to the power n outside. So that's z to the n. Now, if we look long and hard at this integral, it's again Cauchy's integral formula for the derivative. So that's simply, there's an n plus 1 there, it must be the nth derivative, fn at 0. And now, is that the term we want, the term in the Maclaurin series? No, I've made a mistake. It's not quite right because I've forgotten the n factorial. There must be an n factorial in Cauchy's integral formula for the derivative. Now I'm right. See, you can check you're working as you go through in this sort of way. So I now know that this set of terms here gives me the Maclaurin series. I've now got to check that the remainder tends to 0. So let's look at that term now, the remainder term. Right, here it is. There's the remainder term. Again, it looks fairly complicated, but it's not really unmanageable. All the bits can be coped with in piece by piece. Look at Rn. Now, how are you going to deal with that? Show it's small. Well, to show that an integral is small, to estimate it, you've only got one choice. You've got to use the estimation theorem. So that's less than or equal to, now we need an upper estimate for the integrand times the length of the contour. Well, there's a 2 pi I outside, so that gives us immediately a 1 over 2 pi. Now, this expression. Well, the f of w, remember we're integrating round a circle. So it's a circle centre of the origin. W is a point on any point on the circle. This function f is bounded on there, so we can replace f of w, the modulus of that, by m. Now the z over w term, well, the modulus of that is mod z over mod w. Well, of course, mod w is constant because it's a circle, so let's suppose the circle is of radius rho. Then we've got mod z over rho, and all that lot is to the power n plus 1. Now, you want to look after that term. That's the term which is going to make the whole thing tend to 0, because mod z is less than rho, so this is something less than 1 to the power n. That's the thing that's really going to do the trick for you. Now, the last bit is an upper estimate for 1 over all this expression at the bottom here. Now, this is a tricky bit for students, actually. You want to upper estimate this whole thing, you've got to lower estimate the bottom. You want a lower estimate for that. So the next step is to look at the modulus of w into 1 minus z over w. We want a lower estimate for that. Well, I mean, it's better to put it back to what it was before we started this lot. 1 over, divided as mod of w minus z. We want a lower estimate for that. Well, what does it mean? It means the distance from w to z. Well, z is any point you like, any fixed point inside this disk. And what's the smallest value that the distance from w to z can be? Well, w runs around this circle, and the closest it gets to z is when w is there. And what's that distance? Well, that distance is mod w minus z, and it's in fact rho take off mod z. So this is greater than or equal to rho minus mod z. So that's the lower estimate we want for this bottom bit. So in there goes rho minus mod z. Now we've only got to remember the length of the contour, and that's a circle, so that's easy. 2 pi rho. Now everything's fixed here. The whole lot's fixed except for this term, the one I mentioned before, mod z over rho to the power n plus 1. So now all we've got to do is to let n get larger and larger and larger. That tends to 0 as n gets larger and larger. And that's it. But you see, you don't really have a choice. Once you've got the right starting point, as long as you remember that, the thing carries itself along. Each of the steps is more or less inevitable. All right, let's have a look at another example.
Well, that was a theory type question. To finish off the program, let's look at another example. Right, so we're asked to evaluate that real integral. Now, we've asked you to do the details in the broadcast notes, but I just want to talk about some of the highlights of getting a solution to this. Now, I'm trying to solve a real integral, so I know I've got to do it by means of a complex integral. Now, where did I first see that type of integral? The 0 to infinity gives it away. It was in Unit 10 on the calculus of residues. So that I know that I'm going to use the residue theorem. That means I've got to look for a particular complex integral and evaluate it around a certain contour. Now, unless you're given a hint, the odds are that that contour is going to be a semicircular one. So I can start off as follows. First of all, my complex integral is this one. I've just replaced the x by the z. And this is the residue theorem. My contour is going to be a semicircular one, but I've got to be careful. I'm dealing with a log, so I have to take a bite out of the contour around the origin. Now, the next thing that I notice is I'm using the residue theorem, so I have to work out the poles. I find that there's a pole at IB, and that's the only one that's inside this contour. So the next step, and notice that each step as you put it down is getting you marks from the examiners. The next step is to calculate the residue at this pole, and I've just got to be a bit careful because I'm, again, got to choose the right value for log. Having done that, where do I go from there? Well, again, it's an inevitable step. What I've got to do is split this integral up into the integral along that line and around the semicircle, along that line and around the little semicircle. And again, as Graham said, you just shove and thump this thing around because you know that inevitably you're on the right track now. You know that when you look at the integral around these two semicircles, that with a bit of luck you're going to get them to vanish as you let the radius go to infinity and the radius of the small one gets smaller and smaller. So all you've got to do is take a bit of care again with log, and then the final bit is the integral along these two bits of line, and you're pretty sure that they're going to add up to give you the integral that you're after. And all you've got to do is take a bit of care with the parameterization along this line. In this case, you can use z is t e to the I pi. Right, well, as I said, the details, we ask you to go through the details in the broadcast notes. But all I want to emphasize is the fact that once you've got a starting point, then the theory sort of rolls along and the algebra almost takes care of itself.
Well, the message of the program is this. When you're revising, try to pick out the really important points of the proof, and just remember those, and you can fill in the algebra between those important points yourself. It sort of rolls along by itself once you've got those important points. And incidentally, those are likely to be the points that the examiner gives you the marks for. Well, good luck with the exam, and we'll see you perhaps in another course next year.